Listen to anybody who tells you otherwise. Divergent series are not bad. In fact, you're going to see in this course that they are good. Okay? They're very useful, and you will see that they converge much faster than convergent series, which sounds like a contradiction in terms. But what I mean by that is, you saw last time how it might be possible to extract information very efficiently from convergent series, and that it might be possible to extract reasonable information from divergent series. Well, the advantage of a divergent series is that it's easier to extract information from it than a convergent series. That's an interesting fact. It lets go of its information faster. Okay? It's easier to dig the information out. And we looked at a number of divergent series. I think we didn't. I think we didn't look at this series last time. Of course, it would just take us a second to do that. If you have the series 1 plus 2 plus 4, and plus 8, and so on, and you'd like to find the sum of the series, it's wildly divergent, of course. Okay, so you can't add it up. But the question is, if we apply a summation machine to it, and we assume that the summation machine will produce an answer, you need to make that assumption. Okay, we'll call the answer little s. Okay, then we apply the additive rule, or the additive axiom of the summation machine. The sum of all these terms would be 1, the first term, plus the sum of all the remaining terms, which is 2, 4, 8, 16, and so on. And then we can apply the linearity axiom that says if you can factor a number out of every term in the series, that you're allowed to do that. So this is 2 times the sum of 1 plus 2 plus 4 plus 8, and so on. Okay. But we're assuming that this summation machine will give an answer, and that the answer is s. So you get the equation s is equal to 1 plus 2s. Okay? And that tells me that s is equal to minus 1. Okay? So the sum of that series is minus 1. Okay? Okay, so I see that you're smiling about that. And I know why you're smiling, of course. You're saying, what? You added up a bunch of positive numbers, and you got a negative number. Okay? And I don't see any reason why that might be a problem. Okay? There's no reason why positivity should be preserved if you add up an infinite number of positive numbers. Okay? You're assuming, once again, some of the basic rules of arithmetic which may no longer be true, namely the ordering property of the real numbers. Okay? You can say the real numbers are ordered. You can say negative numbers are smaller than positive numbers. This sign here is the ordering sign of the real numbers. You give this up as soon as you go to complex numbers. You cannot say that z1 is less than z2 if z1 and z2 are complex numbers. There's no such thing as an ordering. And in effect, what we're doing, although it's hidden in this machine, we're going to get to it very soon. But what this summation procedure that I explained to you last time is hiding from you is the fact that it's really working in the complex plane. Okay? And so naturally, the ordering is going to be lost. Okay? And you could have a sum of a bunch of positive numbers giving a negative number. Okay? That happens very often. Okay? One way maybe you can think about it is if you take this to be the real line, this is the real line x, you can map the real line onto a finite domain. You can do a sort of Mercator projection, right? Here's x equals 0, and here is, you can draw a circle, right here, a circle just resting right on the origin, okay? And then by drawing a line from the North Pole, okay, you can assign every point on the x-axis. You can map that to a point on this circle, right? So here's a number x, and if you just draw a line to x, this line maps the point x onto a corresponding point on the circle, okay? And now what we're doing is we're adding these numbers 1, 2, 4, 8, da, 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 da. It's going all the way out to infinity. What is really happening is that there's a bunch of dots going around on the circle, and they just happen to pass the North Pole, okay? So when you look at the sequence of partial sums, they're somewhere around here, and when you draw the line, you know, the answer is -1. So perfectly. This is not, you're not supposed to take that as some sort of rigorous proof of anything, but you can imagine why it is that the sum of a bunch of positive numbers is a negative number. It's because complex infinity is a unique number, okay? So there are two real infinities, plus infinity and minus infinity, and they're distinct from one another, because there's no way on the real line to go from plus infinity down to minus infinity without passing through 0. But complex infinity is a unique number. There's no distinction between plus infinity and minus infinity at all, okay? So the complex number infinity is a unique number, okay? 1 over 0 is a unique number. It's complex infinity, okay? You know the proof that if 1 over 0 equals infinity, that implies that 1 over infinity is equal to 0? You don't know the proof? Really? Well, you should know it as part of your culture. This is not mathematical physics, but you prove it by rotation. You take this equation here, and you rotate it 90 degrees, counterclockwise. So that reads -10 equals 8, okay? And now you subtract 8 from both sides, so it gives you -18 equals 0, okay? And now you rotate back again. So it gives you, okay? So, all right. I didn't write that on the board. Right. And don't tell Berlinski or I'm in trouble. Okay. All right. Okay, here's another interesting divergent series, a very interesting divergent series. And the question is, can we sum that series? Okay, so let's apply the summation machine. Here's our generic summation machine. It could be Euler, it could be Borel. We don't know. It's just some sort of summation machine. And we apply it to the series 1 plus 1 plus 1, and so on. Okay? And we assume that we're going to get a finite answer S, some answer S. Okay? And now we apply the additive axiom, the same axiom that we applied over here, and we say this is equal to 1 plus the sum of 1 plus 1 plus 1. Okay? So S is equal to 1 plus S. Okay? That's the equation that little s satisfies. So what do we conclude? What's the solution to that equation? There's a unique solution to this equation. Sorry? Infinity, right. S is infinity. So that's fine. That's perfectly okay. There's no reason why a series should not be equal to infinity. I mean, if this series is going to be equal to -1, why shouldn't that series be equal to infinity? Okay? Now, you might say, wait a minute, every number in this series is smaller than every number in this series, except for the first number. Okay? They're all smaller. So why is this answer bigger than that answer? And once again, you can't use bigger than or smaller than arguments when you're talking about divergent series. Ordering is completely out the door. Yeah?
So we're going around the circle and we didn't reach around it.
Exactly. The way I can think about it is you didn't quite get as far, okay? And so you went around that circle and you wound up right at the North Pole. Just happened to be sitting right on the North Pole. So the answer came out to be infinity. It's a perfectly acceptable answer for the sum of a series. Infinity. That's fine. Okay? And I think we did talk about this series. Okay? So these are some examples of divergent series. And I haven't argued yet that there's any meaning to what we're doing. I've merely tried to argue that there is a reasonable and sensible and axiomatic way of converting a divergent series into a finite number. Whether that finite number has some additional meaning, we don't know yet. That we really don't know. Okay? Okay. Now, again, I want to emphasize that some divergent series really do add up to infinity. And this is an example of a series that is really equal to infinity. In fact, this series is zeta of 1. And the question is, do you know what the zeta function is? Are you familiar? Let me just in case. So zeta, okay, zeta of z, zeta of some number z, is the sum from 1 to infinity of 1 over n to the z power. Okay, that's the zeta function. Very fancy function. Okay, so for example, zeta of 2 is, the sum of the reciprocals of the squares, which is a series we talked about. So it's 1 plus 1 over 2 squared plus 1 over 3 squared plus, and so on. And this happens to be equal to pi squared over 6. Okay? And zeta of 4, 1 over 1 plus 2 to the 4 plus 1 over 3 to the 4, and so on. That's equal to, anybody know? That's right, pi to the 4 over 90. Pi to the 6, zeta of 6 is pi to the 6 over, ha! I win. Okay, and it's interesting that zeta of all the positive even integers has the form of that power of pi, okay, that is zeta of 6, has 6 pi's in it, pi to the 6th power, times a rational number. Just a simple rational number. And that's true for all of the 2n. Zeta of 3, however, is not a simple number. Okay, you can't express zeta of 3 in terms of pi's and other transcendental numbers. It's just apparently, a new transcendental number by itself. So zeta of 3 is equal to zeta of 3. Yeah, 1.2. It actually has a name, somebody's name, Apgar or something like that, has a Apgar's constant or some stupid thing like that. But it's just a number. And nobody knows a simple way like this of writing that number. Okay, maybe there is some simple way, but nobody knows. Yeah?
So zeta of 0 is that series?
Yes. So what I'm getting to is this thing here is zeta of 1. Okay? Now, the function zeta of z is an analytic function of z. Okay, it's a function of complex z. Z doesn't have to be an integer or a real positive number. It can be any complex number. And it so happens that the function zeta of z has a singularity at z equals 1. Okay, and zeta of 1 happens to be infinity. That's perfectly okay. I have no problem with that. But what is interesting is that zeta of 0, by this definition, zeta of 0 is not also infinity, which is very interesting. Okay, so if you calculate zeta of 0, you get something like minus 1/2, which is very interesting because we just argued that our summation machine concludes that it's infinity. And that says that defining the sum of a series by analytically continuing the zeta function, that may give you a finite number, but the zeta function, this is called zeta function summation, does not respect the two axioms that we assumed for our generic machine. Okay? So there are summation machines like zeta function summation, which do not respect those two axioms. So in fact, you're free to make up additional summation machines, and you can make up your own axioms. So this is a very interesting branch of mathematics. It goes under the name of summation theory, and it's quite interesting. Okay, so now I showed you something here. Okay, and you'll notice I just wanted to make a brief remark about zeta summation. Talked about that. Okay, so just to show you, if you calculate zeta of 1, you get infinity. I have no problem with that. Zeta of 0 is minus 1/2. So this is a different result that we get from our summation machine. And that's very interesting. It says that you can build a summation machine that doesn't want to respect all of the axioms. In particular, it's the axiom of well, it's both axioms. The zeta function procedure does not respect the summation axiom, and it doesn't respect the linearity axiom. Okay, it just produces its own answer. Okay, and zeta of minus 1, which would be 1 plus 2 plus 3 plus 4, and so on, comes out to be minus 1/12. That's the answer. So again, a sum of a bunch of positive numbers can come out to be negative. But if you apply the summation machine to this series, you will get, clearly, you will get a divergent answer. Okay? Yeah?
So how do you calculate these?
How do you calculate, sorry, how do you calculate this?
Yeah.
By analytic continuation. Okay? So, in general, when you're defining a function, let's put it this way. Yeah, this is, I'm glad you asked that question. So, a function is an abstract concept, okay? We have a space of functions, just the way we have a space of numbers. The real line has numbers on it. There is a space of functions. The space of functions is, of course, much, much bigger. The number of functions is much, much bigger than the number of real numbers. Okay, it's a higher infinity. You know that, number of curves. But the question is, you know, here is this enormous space of functions. There's one of the functions, f of x, in this space. Okay. How do I, if I say, if you and I want to discuss a function, how do I tell you what this function is? So the only way to tell you what this function is to give you a representation of that function. Okay, so this, right now, this function only has an abstract existence. and it has a number of abstract properties, or it may or may not have. For example, it may be continuous, so therefore it's in the space of continuous functions. It may be once differentiable, it may be twice differentiable, and so on. These are all abstract properties. But if you and I want to actually discuss this function, especially as physicists, because we think this function represents the number of the density of an electron gas or something like this, okay? Then we have to write down a representation. Okay? So how do we write down a representation? Well, the simplest way may be to write a finite algorithm for computing the function. For example, I might say this function is equal to 1 over 1 minus x. Okay, so long as x is not equal to 1. This is one way to represent that function. Now you and I can discuss the function, except we can't talk about the function at 1. But for all other values, in fact, for all other complex values of x, we can discuss this function. Okay? But I might give you another representation of the function. I might say the function is represented by a series of the form x sum from 0 to infinity x to the n. Okay? Now, this representation is only valid when x is in absolute value is less than 1. Okay? If x should be 1 in absolute value or more, that's it. Yeah, that's the series representation. Okay? Now, so this representation only works for a limited number of values of x. So here's the whole complex plane, but this representation only is valid inside, not on the rim, but inside this circle of radius 1. Okay? Now, another example would be gamma of x. That's a very, very fancy function. Do you know what gamma of x is? Everybody know what it is? This is essentially the factorial function. Gamma of x is the integral from 0 to infinity dt e to the minus t to the x minus 1. Okay, you know that. And you know that gamma of x, if x is an integer, gamma of n would be n minus 1 factorial. Okay? Now, this is called the Euler representation of gamma of x. So there is, in function space, an abstract function, gamma of x. Okay? In order for us to talk about it, we need a representation of the function. Here's one way to represent the function. Okay? But this way has the problem that it only exists for x, for the real part of x, greater than 0. Otherwise, this integral diverges. That doesn't mean the function doesn't exist. It just means that this representation is not valid unless you are in this region. Okay? So gamma of minus 1.3 exists. But you can't calculate it using this representation. You need a different representation. Okay? And there are many different representations. There's an infinite product representation. There is another integral representation that exists for negative values of x, and so on. There are dozens of different ways to represent the gamma function. And they all are valid in different regions of x. You beginning to see what I'm saying? So the problem here, now I'm going to answer your question, how in the world do we calculate zeta of 0? Okay, well, clearly this representation won't work because this series doesn't exist. So this series exists so long as the real part of z is greater than 1. Okay, otherwise this is not, this I can't use an equal sign here. Okay, because if this is equal to something that doesn't exist, then you're saying this doesn't exist. Okay? So the zeta function exists as a function, But this can only be used to calculate the zeta function when the real part of z is greater than 1. However, we can convert this into an integral representation, which you can look up in a book. And then that integral representation may be valid when the real part of z is negative. Okay, so we evaluate the integral. Yeah, you have a question?
Didn't you say a few minutes ago that a sum that doesn't converge and converges to infinity is just fine?
Sure.
So,
sure. And
therefore,
in fact,
how can you say that
so
this representation doesn't exist just because it gives you infinity?
oh no, that's the
not
point
what you're
is
saying?
that the point is that as a series, this series converges when the real part of z is greater than 1. Okay? If the series does not converge, that does not mean the function is infinite. But I'm defining this. So how do I begin? How do I start out to define the zeta function? I write down something that exists. This sum exists as a sum, as an infinite sum. That is, it has a life of its own and it converges. Therefore, this is a valid representation when the real part of z is greater than 1. Okay? Now, does this say anything about zeta of 0? No, it doesn't. So now we have to do a lot of work, and we have to analytically continue. So this series exists in this region, in the complex z plane, greater than 1. Okay? Now, in this region, we convert this series into some sort of integral representation. And that integral representation may exist, for example, at -1, and we conclude that zeta of -1 is minus 1/12. Okay? Now, we then calculate, we can use one of these representations, okay, to calculate what zeta of 1 is. And zeta of 1 has a singularity, okay? That we know. There is no singularity at -1 or at 0, okay? But right here, zeta has a singularity in the complex plane, okay? And so it really is infinite at that point. Okay, so the function that this abstract function that we're talking about is really infinite there. Yeah?
And how do you know that?
Because I calculate, I establish that zeta of z is an analytic function. Okay? And that this analytic function has a singularity at that point.
Yeah,
and I can determine the nature of the singularity. And I can see in the complex plane what happens as I approach that singularity. Okay? And I can see that the function itself, not this series, but the function itself is actually blowing up at that point as I approach this point. And therefore I say the zeta function is infinite.
But how do you find out anything about the function itself?
I'm not sure I understand.
How do you get the information of zeta of 1? All you've given us is this definition in terms of the
Right,
series.
by analytic continuation. Do you know, have you learned analytic
sure,
continuation? Okay, so I mean, this is, so I establish, it's not obvious from the series, of course, but I establish that the function zeta of z is singular, that is, it is not analytic at 1. And I can see what happens as I approach 1, and I can see that the function is becoming infinite there. Okay, for example, from this representation, here, let me show you. From this representation, it's much easier to see here. From this representation of the gamma function, which is valid when the real part of x is greater than 0, okay, this definition of the gamma function is only valid in the complex plane in this region. Otherwise, this integral diverges. Do you see why? By the way, why is this only valid? Why is this representation only valid when the real part of x is greater than 0? What's the problem? What happens if the real part is 0?
Divergence of 0.
There's a divergence at 0. That's right. Okay. So now what I do is I say, I would like to study this function for negative values of x. How in the world am I going to do that? Okay? So what I do is I say, I need, this representation is not useful for negative values of x. Let me convert it into another representation, which is harder to remember, but which is useful. Okay, this is easy to remember. Okay, so how do we convert it? Well, I can certainly, if I assume that the real part of x is greater than 0, I can say this is the integral from 1 to infinity, dt e to the minus t, t to the x minus 1, plus the integral from 0 to 1, dt e to the minus t, t to the x minus 1. Do you agree? Okay, so long as the real part of x is greater than 0. Now, what about this integral? How does this integral behave as a function of x? Can x be 0 here? Okay, now there's no problem with the integral diverging at t equals 0 because I'm integrating from 1. Okay, and in fact, this integral exists and defines an analytic function. This guy is an analytic function of x for all x. It's analytic. That means it has a Taylor series for all x not equal to infinity. Okay, for all x, all finite x. Okay, now what about this? That's where the trouble is. So I've isolated off the trouble here. But on the range from 0 to 1, it is perfectly valid for me to write e to the minus t as the integral from 0 to infinity minus 1 to the n, t to the n, over n factorial. You don't have any problem with that. I couldn't have done that in this integral because this series representation is not valid at t equals infinity. But this series representation is valid on the range from 0 to 1. You see that? Okay? Now, let's look at this series. This is a uniformly convergent and absolutely convergent series. Okay? And it is absolutely justified for me to interchange orders of integration and summation. Okay? Because of uniformity. And therefore, I can write this guy as the sum from 0 to infinity minus 1 to the n over n factorial integral from 0 to 1 dt t to the x plus, t to the n plus x minus 1. Yep, okay. And now I can integrate this easily, and I get t to the n plus x over n plus x. You with me? And I have to evaluate this from 0 to 1. And at 0, this vanishes. And at 1, this is equal to just 1 over n plus x. And therefore, this sum is the sum from 0 to infinity minus 1 to the n over n factorial n plus x. Okay? Now, this sum exists for negative x. So I have extended the original representation, which is easy to remember, to another representation, which is valid when x is negative, except when? Except when x is a negative integer. Okay, x better not be minus 3 or minus 5 or minus 4 or 0. Okay, so that tells me that, so this exists for all, so this exists and converges and defines an analytic function because it satisfies the Cauchy-Riemann equations. Okay, for all x not equal to 0, minus 1, minus 2, and so on. Just so long as x is not that. So everywhere in the complex plane, we have now established that the gamma function is an analytic function. Why? Because this is an analytic function. How do you know it's an analytic function? Verify it. You can differentiate it and show that it satisfies the Cauchy-Riemann equations. Okay? And this is an analytic function. Okay, and now we're going to answer your question, finally. What happens as we approach one of the singularities? Okay, so we can ask what happens as x approaches, for example, 0. And everything remains finite except for one term in this series. And the one term in this series is 1 over x. So we know that gamma of x is asymptotic to 1 over x as x goes to 0. Gamma is a terribly complicated function. But using asymptotics, I know that everything is negligible. Everything is negligible in that sense as x goes to 0, except for the very first term in this series, which is just 1 over x. So gamma of x behaves like 1 over x as x goes to 0. Therefore, it's infinite. And the same kind of analysis, but it's more difficult. You'll have to go and look in a book if you're interested. With the zeta function. As z approaches 1, zeta diverges just in a similar way, like to this, except this is a linear divergence, that divergence is a logarithmic divergence, okay, because it's the sum of the reciprocals of the integer, so it goes like 1 plus a half plus a third, so it blows up logarithmically, okay, but it's infinity in the same way that this is infinity. And it's perfectly okay to say that gamma of 0 is infinity. Nothing wrong with that. Gamma of 0 is indeed infinity. Okay? Perfectly valid value for a function at a point. Infinity. Okay? So that it was a long answer, but do you see what I'm saying? Function theory is pretty interesting because we don't think about functions usually in the abstract. We think about functions in terms of representations which we can play with, we can differentiate and calculate and so on. Okay? And what we're getting to in just a short time is the idea that one possible way of writing down a representation of a function is like this. F of x is represented by this series, sum from 0 to infinity, a sub n, x to the n, let's say, not as an equal sign, but using this symbol. And this is an asymptotic representation of the function. And you're going to see that this is extremely useful. Until now in your life, whenever you've written down a representation of a function, you've used that symbol right there, or that symbol, the equal sign. But we can just as easily represent a function by something that doesn't exist as a sum, but does exist as an asymptotic series. Okay, that's what we're getting to. Okay, this is a very, very subtle point. Are you beginning to get the content here? What I'm arguing is that there's a new way to represent functions and to represent them without equal signs, but to represent them with objects that appear naturally when we do calculations in physics, namely perturbation theory. Okay? So, yeah, T-Bar.
Just a comment that gamma was -1, some -112. In
Zeta.
Sorry, zeta.
Yeah.
That's a very important value series in physics, right?
Yes, it is. So, in fact, in physics, this and this appear very often. Do you happen to know where these things might appear? Who's?
String theory.
Yes, that's true. They do.
In force calculation.
I wasn't going to say something as abstract as that, but I mean, there are lots of times when you put, in order to make sense out of a physical theory, you put a particle in a box, okay? And instead of having a continuous set of energies, you now have a discrete set of energies, and these energies are called modes. So on a string, if you're talking about string theory, you now have a set of modes. If you want to find the total energy, you need to sum over the modes. And this appear very often in physics in modal sums. And when you don't know how to calculate a divergent sum over energies, you do like that. And you say zeta function summation implies that, okay? Whether or not that's valid, that's a very tricky thing to do. That's very, very tricky. Yeah?
I think the computation of the Casimir energy is
Exactly.
another example.
So when you calculate the Casimir energy, so do you know, how many of you know about the Casimir force? You do? Oh, forget it. I was going to say something. Okay, so when you calculate the Casimir force, you need to sum over modes. Why is it, for example, are any of you ship captains by any chance? Any of you had training as a captain of a ship? No. If you had training, you do? You know?
I have the boat lessons. But
good. Okay, then you know. Excellent, excellent. Okay, then you know that if you have an ocean liner here, okay, big ocean liner, okay, you should never, ever, ever park it, at a dock. You should never put it next to another ocean liner. You should never do that. Do you know why that is? Do you know why that is? It's because of the Casimir force. It's because there are modes. This is a finite region here, okay? And there are modes, there are wave-like modes that are established between here, and there are wave-like modes here, okay? And you can ask, what happens to the total sum of the energies of the modes? If we sum over all the energies, we find the total energy, okay? If we then vary that energy with respect to distance, the derivative of the potential with respect to the distance is a force, and this force here will actually turn out to be negative, okay? So there is a force that pushes these two boats together, and they will bang into each other, inevitably. And I think this happens in a James Bond movie, isn't that? I think it does, doesn't it? Or maybe it's not a James. It's one of those action movies where the guy is being chased by another guy in a boat, and James Bond, I think it's James Bond, knows all about the Casimir force, so he races through here and comes out the other side in his speedboat. But the two boats are coming together, and he just makes it. The other boat goes inside, and it gets trapped here, and all right, never mind. So that's the Casimir force. Casimir force really has nothing to do with quantum mechanics necessarily. It's not only to do with, what I mean is, it's not only to do with quantum mechanics, it's just a sum over modes and establishing that there's a force, okay, because of the sum over modes. Okay, so let me give you, yeah.
So the gamma function is kind of a continuation of the factorial function.
That's right.
There's a lot of different functions you can come up with
that would do that.
That match the factorial
Yes,
on the real
okay,
number.
but let me interrupt you for a second. An interesting problem that people thought about when they, obviously there are many such functions, okay, but the question that people were asking this is back in the 19th century and the 18th century when they were thinking about questions like this. An interesting question is how much information do you need in order to have a unique analytic function? So we would like to have a unique analytic function, call it gamma of x, which has the property that gamma of x is equal to x minus 1 factorial if x is an integer n, okay? If x is a positive integer. If x is, 1, 2, 3, like that, okay? And there's an answer to that question. And there's a very simple answer, okay? And basically, it has to do with knowing the asymptotic behavior, okay? So once you know that the factorial function, gamma of x, goes like x to the x e to the minus x over the square root of x times square root of 2 pi as x goes to plus infinity. Once you impose that, it's unique. There's only one function.
So, I mean,
So this is one way of specifying that function uniquely.
yeah. So, for example, like for the zeta function, you have a defined find for all real z greater than 1.
Right.
And that's enough information to analytically continue to the rest of the plane.
That's correct.
And so, what exactly does analytic continuation mean? Because there is an infinite number of different functions with which you can continue them.
Zeta function is different than factorial.
Yeah, I know.
In fact,
I know.
so
I'm not
remember,
connecting
no, he knows that.
The question.
I agree.
No, so
Yeah.
The question is, if you take the zeta function where it's defined,
Mhm.
and then in the other part, I mean, in principle, you can have any kind of oscillations, anything you want, right?
Right. But
So how do you?
But analytic
does-
continuation
yeah,
is
what
analytic continuation is a unique process.
Yeah.
So if you define a function by starting with one representation, and that representation defines an analytic function, then you can analytically continue, and that process of analytic continuation produces a unique result.
So it's essentially
Okay.
like
Now,
this-
why is it that analytic continuation works? Because, and that's what he was beginning to tell you, this function zeta is defined on a continuous range of z, and therefore it defines an analytic function. This definition, starting with a factorial function, that factorial function is only defined on the integers. So there are many ways of analytically continuing off an integer. The reason is that in principle, you could say, look, if I begin by saying, I want to know what is gamma of x, but I begin by telling you that gamma of n, when n is a positive integer, is n minus 1 factorial. This doesn't say very much, because I could add to it, I could add to whatever function I construct. In principle, I could add sine of pi times x, because sine of pi n is equal to 0. So I could add something to it that vanishes. That's the reason why, if you're just defining a function on the integers, that's usually not enough information. Okay, that's why this is an interesting problem. And furthermore, once this vanishes, I could multiply it by any other function of x. Okay, just some random function of x. Okay, so I'm adding 0 to it on the integers. So therefore, this uniqueness problem is an interesting problem.
Right. So with the analytic continuation, there exists only one analytic function that equals to
Right,
that on the.
right. But once you're defining the function on the integers, that's not a terribly unique way. That's why people back in the 19th century thought hard about the uniqueness issue. Okay. All right. So here is a very standard example. And this is the quintessential example with regard to physics. Okay? So here is the physics problem. Okay? Now, in fact, let's use this. Okay. This is a model problem, and it is like essentially any problem that you might encounter in physics. You encounter a very hard problem in physics. Okay? An example of a hard problem is the anharmonic oscillator. So the Hamiltonian h is equal to p squared plus x squared plus epsilon x to the fourth, or plus x to the fourth. This is the anharmonic oscillator. Okay? And I can put in, I like numbers like that, but it doesn't matter. Okay? So this means, so your physics problem, should you wish to accept it, your physics problem is to solve the differential equation d squared dx squared plus x squared over 4. So this is the physics problem is solving h psi equals e psi. So this is the abstract statement of the problem. Your real statement of the problem is to solve this differential equation. Okay? That's your problem. And the boundary conditions are that psi of x goes to 0 as x goes to plus or minus infinity. That's your problem. Nobody knows how to solve this problem analytically. It's much too hard to solve. So what do? You say, I have one analytical tool at my disposal. I will insert an epsilon over here. Okay? Now you have reduced the hard problem into an infinite sequence of easy problems. Okay? Easy problem 0 plus easy problem 1 plus easy problem 2, and so on. And you solve those problems. Got it? So now you have found the coefficients. What this tells you is that E of epsilon is the sum of a sub n epsilon to the n. So you understand the logic. You are faced with a hard problem. The only way you know how to make analytical progress is to introduce a perturbation parameter, and you end up with this series. But unfortunately, you find out that this perturbation series, a sub n, is a divergent series. In fact, a sub n grows roughly like a constant times 3 to the n times n factorial times minus 1 to the n plus 1, okay? As n goes to infinity. So you can't write an equal sign because it isn't equal to that, but it is asymptotic to that. Now, I haven't yet defined for you what is meant by an asymptotic series, but nevertheless, that's what you have calculated. Okay? So you have a representation of the answer. And that representation is not like this one, or like this one, or like this one, because all of these representations are equal to the function. Your representation that you've found is not equal to the function. It's asymptotic to the function. But it's not equal. It can't be, because this doesn't exist. Nevertheless, just the way you can sum this series and calculate the answer, I'm arguing that we can sum this series with arbitrary precision. So you now use a summation machine, some kind of summation machine. You sum this series, and you can find the answer, namely, that is, i.e., E, for any value of epsilon. Any value of epsilon. And there it is. This is the outline of the course that I'm teaching you from start to finish. Done. That's it. And the hard part is what we're getting to right now. How do you do that? Okay? So I'm claiming that this, while it doesn't exist as a series, does exist as an ordinary convergent series, does exist. It has an existence, well-defined mathematical existence as what is called an asymptotic series. And this asymptotic series can be summed using a summation machine, and it can produce the answer with arbitrary accuracy. What I mean by arbitrary accuracy is you give me some tolerance. You say, I want the answer. I want to know the sum of this series correct to 1 part in 10 to the 10. I go chugga, chugga, chug, and I give you the answer correct to 1 part in 10 to the 10. You say, no, that's not enough. I want it accurate to 1 part in 10 to the 15. I can do that. No problem. There's no upper limit. There's no bound on how accurate I can produce the answer. So I can give you an arbitrarily accurate answer, but I cannot tell you the answer. Okay? Because it's not a solvable problem. Okay? Okay. Questions about that? Okay, so the question is, how are we going to sum divergent series? And let me tell you what the real problem is here. What is the problem that we really face here? Do you know what I'm getting to? We have a really serious problem. That's the reason for giving you a whole course on this topic. The problem is that in all of the games we've played, we've said, what is the sum of this series? This is 1/2, and so on. The sum of the series is 1/2. We had an advantage here. The advantage is that we pretended that we knew all of the terms in this series. So for practice, we studied series where we knew every single term in the series. But in real life, when you have a physics problem like this, you don't know all the terms in the series. That's because while I have reduced this to a sum of easy problems 0, 1, 2, 3, in general, this takes you 5 minutes to solve, and this takes you an hour to solve, this takes you an afternoon to solve, okay? And the next one is 1 week, and then you give up. Okay, so typically, we only have a finite number of terms in the series. And because typically we only have a few terms in the series, we're trying to sum a divergent series where we only know a few terms. This is a really hard problem. Okay? Okay, that's the reason why this is interesting. Okay, so the question is, what do we do if we don't know all of the terms in the series? And the answer is, we use a continued function technique to sum the series. And I'd like to give you an example. So, do you know what I'm going to be teaching you? The really powerful tool does anybody know the name of it? I don't want to spoil this by trying to give you a rush lecture on what we're going to do. But what we're going to be talking about is Padé theory and Borel's summation. Those are the techniques that we're going to use. Okay, and Padé theory is really wonderful because it's mathematics right at the front line. I mean, it's not completely understood, and many people, it's in some sense, it contains an element of magic to it. So there are lots of theses that have to be written, but it clearly works. Okay, and it can be shown to work rigorously in many cases. In particular, in summing this series, when I say I can produce an answer which is arbitrarily accurate, this is a rigorous result. It takes several hundred pages of really careful mathematics to prove it, but the techniques that I'm going to show you actually work rigorously in this case, and in general in quantum mechanics. Not just for this case, but in general for quantum mechanics. It rigorously works. Okay? But I want to explain to you what I mean by continued functions. Okay? And I'm going to use, I think, a really cool example. Okay, so this is something I really enjoy. So let's see. Okay. Okay, so what's an example of a continued function? Okay, suppose you have a series representation like this, just like this. This is a Taylor series, and Taylor series have a problem. Okay, they only converge in a circle. So if I say I have a function f of x, and this function f of x only converges in a circle, okay, so I give you the Taylor series representation, sum from 0 to infinity a sub n x to the n, and this only converges in the circle of whose radius of convergence is r. So in the complex x-plane, this is where that series converges. But physics demands that we need to know the value of the function over there, say, which is outside the circle. So I have a function, but the function is represented by a series that doesn't converge where I want to know the value of the function. How can I find the value of the function out here? It doesn't mean that the function doesn't have a value. It has a value there, but this representation of the function is not useful for telling you that value. Do you understand the problem? You all understand this problem? So for example, over here I have a series. Okay? But this series doesn't exist. This series exists only for x less than 1. What if I want to know f of minus 2? Okay? I can't calculate it from the series. So I need a different representation of the function. So one way to get a different representation is to be incredibly clever and to take this series and sum it up. And once I've summed it up, now I can plug in x equals minus 2, and the answer is 1/3. Okay? But this was an easy problem. So I propose that we write this series in a different form. Okay? Now here's a really crazy idea. What I propose to do is to write it in the following form. Let's rewrite this function as a continued exponential. Now it could be a continued anything, but I'm talking about continued functions, and as an example of a continued function, let's write it as a continued exponential. So what's a continued exponential? Okay, so I will write it as b0 e to the b1 x e to the b2 x e to the b3 x e to the b4 x. So it's an iterated exponential. Okay? So I'm re-representing the function. Now, how do you do that? If you know these coefficients, how are you going to learn those coefficients? How would you do that? Well, it's not so hard. You Taylor expand this as a series in powers of x, and order by order in powers of x, you set the coefficients in this series equal to the Taylor expansion of this object. And you get a bunch of algebraic equations. So A0 will tell you B0. In fact, can you tell me? What is B0 in terms of A0? They're equal. Okay? How do you know they're equal? You just said x equals 0. Right? Now, you continue to Taylor expand, and you find that A1 now determines B1, and A2 determines B2. And I've written down the equations, so I'm going to show you what they look like. But this was stupid because I used over here different letters, but that's okay. Sorry about that. Okay. So here is a continued exponential. Here is a Taylor series. If you Taylor expand this and require that Taylor series are unique, okay, then what you learn is that C0 is A0, C1 is A1, A0, C2 is this, and C3 is that. You notice these formulas are getting more and more complicated, but they're all trivial. Okay? And there is a unique way to go from the C's to the A's and from the A's to the C's. Do you all see that? If I know the first 10 A's, I know the first 10 C's. If I know the first 10 C's, I uniquely know the first 10 A's. Why is that? Because if I know C0, I know A0. If I now know C1, and I also know A0, then I now know A1. Okay? Now I know A0 and A1. If you tell me C2, then the only thing in this equation I don't know is A2. Okay, so it's really a linear equation in A2. This is a linear equation in A3. So the answer is unique. So I can go from the coefficients C to the coefficients A. I can go back and forth. Okay, do you all understand that? So now, what would be the advantage of doing this? So to illustrate, here's a simple illustration. Let's take the function. In fact, this is the only simple example I know. That's really wonderful. Let's take the following continued exponential. E to the x, e to the x, e to the x, e to the x, e to the x. In other words, as an example, let's take the case where every b, all the b's, are exactly 1. Now, what's nice about this example is that in this particular case, I know all of the a's, all of the Taylor coefficients, exactly and in closed form. And I'm going to give you a formula for them. This formula is not at all obvious, but the formula is given by the sum from n equals 0 to infinity, n plus 1 to the n minus 1 power over n factorial times x to the n. Okay? This is an exact identity. Okay. Are you with me? You following what I'm saying? So just imagine for a moment that you have done a hard perturbative calculation and you've gotten these numbers. Okay? And we have been able to re-represent, to change this representation of a function into this representation of some function, the same function. I claim that this representation is better than this representation, and I'm going to explain to you why. Okay? So what's the reason that this guy on the left is better than that guy on the right? Well, the question is, where does this converge? Can you tell me what the radius of convergence of this is? What's the radius of convergence of that series? Does anybody know? Say it again? Oh, no, not 0. No, no, no. So we need to know, how does this behave for large n? Right? To determine the radius of convergence, how do these coefficients behave for large n? So what does n factorial behave like, roughly, for large n? Say it again? Okay, it behaves roughly like n to the n. That's right, very important, times e to the minus n, times something less important, times, say it again? There's a square root of n, so there's a minus 1/2, which is unimportant, times a constant, which is the square root of 2 pi. Okay? This is unimportant, that's unimportant. But the geometrical growth and this n to the n growth are important. This is as n goes to infinity. Okay, that's how the gamma function behaves. This is called the Stirling approximation, and maybe we'll talk a bit more about this in the course. But that's how n factorial behaves. So the nth coefficient, n plus 1 to the n minus 1 power over n factorial, behaves for large n, roughly like n to the n. This is roughly like n to the n. Okay? Divided by roughly n to the n e to the minus n, roughly. Okay? Which behaves like e to the n. So the nth coefficient is growing roughly like e to the n. So this series will only converge, this series converges if x is less than what? Say it again? 1 over e, that's right. Okay, if x gets bigger than 1 over e, then when you multiply x to the n times this nth coefficient, it will be diverging, like a geometrical series where the ratio is bigger than 1. You all see that? So this is only valid for x being smaller than 1 over e. So here is the complex x-plane. Here is the point 1 over e. And this series converges in a circle of radius 1 over e. Okay? Now, suppose you needed to know this, the value of this function at, say, -1. -1 is out here. So this is no good. However, we have shown that inside of the circle of convergence, this function is equal to that function. We haven't actually showed it. I've told you that it's true. Okay? And I've found that it's true because if you plug into this formula, you'll see that it's true. Okay? The question is, how do you evaluate a continued exponential? What does that mean? Okay, I know how to evaluate a series. In principle, I just add up the numbers in the series. Or I do better. I use Shanks to improve the convergence, or Richardson or something. Okay? But what about this? How do I evaluate that? Can you tell me?
And I mean, if you assume that e to x is equal to y,
Yes.
then it is equal to e to xy.
Oh, but you're giving me an implicit way to... the point is, you have given me... Let me tell you, you've done something that's very tricky. You have told me a function, okay? You've given me an equation, and you have told me that the solution to that equation is the evaluation of that continued exponential. But in fact, that equation has several solutions. How do you know which solution to that equation is the right one? Okay. In other words, I'm asking you, I need to evaluate this directly. So I claim all you need to do is this. Let's calculate first e to the x. Next, I will calculate e to the x, e to the x. Next, I will calculate e to the x, e to the x, e to the x. And so on. Now that's easy because all I have to do is push buttons on my pocket calculator. Okay, I go push, 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 and so on. And this defines a sequence of approximates. Okay, so I can call this A1, A2, A3. Okay, so I now have a sequence A sub n, and the question is, does this sequence converge to a limit? And the answer is, this sequence converges to a unique limit, not just in this circle over here, or this circle over here, whose radius is 1 over e, but it actually converges in an enormous region, all the way down to minus e. And the shape of the region is beautiful. It looks like this. Okay, this is a cardioid. And inside of this region, everywhere inside of this region in the complex plane, this converges, okay? And therefore, I can calculate the value of the function at -1. I have analytically continued the Taylor series outside of the circle by using a continued function. Okay? So I'm going to show you a picture now. And then I'm going to conclude with a beautiful picture. Okay, so this is the example that I've just shown you. And this is the cardioid. This is where the Taylor series converges. But this cardioid here is where the continued exponential converges. So therefore, I can calculate, say, the function, the value of the Taylor series at -2. Do you see the trick that we used? Isn't that beautiful? So now I want to conclude this lecture, so I want you to have a good weekend, but I want you to dream about the following picture I'm going to show you. Okay? Tibor knows what I'm going to show you. He's seen this before. The question is, outside of this cardioid, this sequence of exponentials does not converge. Just like a Taylor series doesn't converge, this representation of the function also doesn't converge. Okay? But it doesn't blow up. So how could a sequence not converge but not go to infinity? What could it do? Say it again? It could oscillate. In other words, it could converge to two limits. It could approach, it could go and converge to this limit and that limit. Or it could converge to 3 limits, or 4 limits, or 5 limits, or 6 limits, or an infinite number of limits, which would be chaos. Okay? So this is the picture. Okay, so I had an undergraduate student who won the prize for the best undergraduate research in the United States that year. And what he did was he calculated this continued exponential here, this continued exponential, for each pixel on the computer screen to see how the convergence took place. This is the upper half of the cardioid. This is only the upper half complex plane. Okay, so this is the cardioid. You see this red picture? Where it's red, that is where it converges to 2 limits. And each color corresponds to a different number of limits. This has 3 limits. Okay, this has 4 limits, 5 limits, 6 limits, 7 limits, and so on. Okay? There are altogether 12 colors on this picture because after 12 limits, it was too hard for his computer to decide, okay, whether or not it had converged, how many limits it had converged to. Black means he couldn't figure out. I mean, the computer was not strong enough to determine what it converged to. Notice that each of these regions looks like the head of a tadpole, but the tail of the tadpole is missing because it's too delicate. The computer couldn't determine it. But in fact, each of these regions is infinitely long. See, there's a little crescent over here. That's because the computer could no longer make a decision. But in fact, this region has a tail that's getting exponentially thin, and this tail goes all the way out, runs parallel to the real axis, and goes all the way off to infinity. And every single one of these regions has a tadpole-like tail, infinitely long tail, and these tails do not cross each other. So, for example, you see this little tadpole, the head of the tadpole? It has a tail that comes out through here, and out through here, and out through here, and out through here, and all the way out, and it goes all the way out here. Okay? And you see this little region here, this has a tail that goes out through here, out, all the way out through here. So there are infinitely many regions here. You can see this has a fractal structure, obviously, right? And each of these little patches has a tail, like this purple patch here has a tail that comes out through here, out, all the way out, and goes out to infinity. Okay? So when you have a continued fraction, the nature of the convergence, I don't mean a continued fraction, a continued function. When you have a continued function, the nature of the convergence becomes immensely interesting and immensely complicated, and it can have fractal structure. Okay? You notice this red area comes along like this, and it has a little dimple over here. See the dimple? Comes in, it has a little cusp over here, and comes back out again. That's a reflection of this cusp over here. And you notice all of these regions have little cusps. Cusp, 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 cusp. Okay? And they are all sons and daughters of the more elementary regions. So this is the first region, which has only one cusp. And then that cusp is reflected over and over again in this red region that's going all the way up to infinity. And that is reflected by all these little cusps in all of these regions. They have all little indentations. It's fantastic. Okay? So I'll let you dream about that over the weekend. But next time we're going to talk about something, this is very elaborate. Okay? You could make a continued square root. You could make a continued cube root. You could make a continued logarithm. You could do something like re-represent this function, not this way, but as the square root of 1 plus a times x times the square root of 1 plus b times x times the square root of 1 plus c times x, and so on. And now you have a continued square root, and for sure this would converge in a region that may be larger. Very likely that this thing converges as a continued square root in a region that's larger than the circle in which the Taylor series converges. Okay? Or instead of square root, you could have log of 1 plus ax times log of 1 plus b, continued logarithm. Next week, we're going to be talking about the most important continued function, which is a continued fraction. Okay, and continued fractions are the most popular way of summing a divergent series. Yeah, Tibble. Does
this set have a name like a Mandelbrot set? Or?
This has this is not a Mandelbrot set, but it's related to a Mandelbrot set. There's a tremendous amount that's unknown about this picture. The most interesting question is, you see, black means he couldn't decide. The computer was not strong enough to decide. Of course, this was several years ago, and computers are faster now, so we could make a better picture if anybody's interested. Okay? But the question is if you make a better picture, is there any black left? That is, are all points in the complex plane, do they all have a finite number of limits, or is there a set in here that has an infinite number of limiting values? Okay. Do some black points remain? I don't know the answer to that question, and it's not known. And this is a really, really interesting, if you like just interesting pure/applied mathematics and computer, numerics and things like that, answer that question. I don't know the answer. Okay. But it's astonishingly beautiful, isn't it? Okay. So have a nice weekend, and next week I will show you how to sum a divergent series in a meaningful way, and I will show you that